So now we want to move on to something a little bit different, that is relative motion analysis. The basic idea here is when two things are moving, it's sometimes convenient to be able to understand the motion of one particle relative to the other moving particle. And so we'll look at a few examples that walk through that. So the essential idea is we're combining a piece of information about motion. Sometimes it's relative to a static system, sometimes relative to a moving system, and putting it all together to, solve some kind of problem. So as kind of a model problem, suppose there's a rail car here that's traveling along this track at a certain angle from a road, and the person on the rail car wants to shoot some projectile at the person on a moving target, and this moving target is moving along this road. Okay, so the shooter knows the speed of the projectile as it leaves the moving gun. So you know the speed relative to the moving gun, not relative to the road. And it turns out that by understanding the distinction between the two, you can figure out how to aim so you hit the object. Okay. And you could answer questions like if you're on the ground, what would you measure for the speed of the particle of the projectile, that sort of thing. Okay, so we think of it like this. We have a static system, xy, which is stationary, and the xy here are capital. And then on particle A, there's a coordinate system moving with the particle, and that's little x and little y. So this little x and little y system is moving at the same velocity as A. For this discussion, we'll assume that it does not rotate. So if this coordinate system is rotating, things get a little more complicated. But we just assume it's translating. So the little x is always parallel to capital X. Little y is always parallel to capital Y. And this coordinate system is just translating. Okay. So for example, we might want to know this relative position vector. That is a position vector of B relative to A. So it's kind of like both ends of the position vector are moving. We can write this in terms of the coordinates of the stationary system. That is that the position vector B relative to A are the difference in the coordinates relative to the static frame, xb minus xa in the I direction, and yb minus ya in the j direction. Okay, so this is just defined by the difference in the x coordinates of the two particles, which are both a function of time, and the difference in the positions of the particles, and again, both are functions of time. But we can also write it in terms of these x and y coordinates of this moving system. So if we're if you think of yourself as sitting on particle A and the coordinate system is moving with A, then the origin is always on A, and B relative to A is just defined as the coordinates of B in this little x, little y coordinate system. So it's little x of B in the x direction and little y sub B in the y direction. Okay. And so these are two different ways to write the relative position vector of B relative to A, and these things should give you the same result. Okay. So RB then is just RA plus RB relative to A. So in the little x little y frame, that is in the moving frame, RB sub A relative to A dot, that is the time derivative of this relative position vector, is just the time derivative of the x coordinate in the moving frame and the y coordinate in the moving frame. That is little x dot and little y dot. In the stationary frame, RBA, RB relative to A, the time derivative of that is just xb dot minus xa dot in the x direction plus yb dot minus ya dot in the y direction. And then we can write these terms in the moving frame. Okay. notice that this I hat dot and j hat dot are both 0 because those vectors are not changing in magnitude. They're unit vectors, and they're not rotating because we assumed this little x, little y coordinate system is not rotating. So that's important. So both those time derivatives are 0. And therefore, the time derivative written in the little xy frame is the same as the time derivative in the capital XY frame. That is, the time derivative in the moving frame is the same as the time derivative in the stationary frame. Okay, so if we write the velocity of particle B is the velocity of A plus VB relative to A, and the acceleration of B is the acceleration of A plus the acceleration of B relative to A. So as long as this moving system is not rotating, then the velocity and accelerations are the same no matter which frame you're in. Okay. So quite often we use constraints to simplify problems like this. So suppose we have this pulley system. So there's a rope attached at A, it goes around this pulley at B, it goes over this pulley at H, and that's hanging at a fixed distance from the ceiling, and then it goes down here to this block. And suppose we want to find the velocity of this block P relative to the velocity of this block Q. We can do that with constraints. So what we want to do is write the total length of the rope that's used for these pulleys, and we assume the rope is not stretching, so its length is fixed, and we can use that as a constraint to help solve a problem like this. Okay. Since this block P is attached to this pulley with a cord of fixed length, then the velocity of P and G are the same, and the acceleration of P and G are the same. And then since this pulley is attached to the ceiling with a rope of fixed length, then this pulley has 0 velocity and zero acceleration. It's completely stationary. So we can write the total length of the cord from this point to this point as the length AB plus the length going around this pulley plus the length CD plus the length going around this pulley plus the length EF. Okay, and the length around this pulley and the length around this pulley are fixed, right? They're half a circumference of the pulley, and so they're constant and they will have 0 time derivative, right? So we can define yp as the position of P relative to the ceiling and yq as the position of Q relative to the ceiling. So the distance AB is yp minus this distance ig. And the distance CD is the distance yp minus ig minus jh. Jh is this up here. And then the position the length EF is YQ minus JH. So L then from up here can be written as twice YP plus YQ minus 2GI minus 2JH plus these pulley half circumferences. So the constraint is that the rope doesn't stretch. So the total length that we've just written down is constant. So L dot is 0. And since those pulley lengths, several of those lengths are constant, then L dot is just 2YP dot plus YQ dot, and that has to be 0 because L is fixed. Okay, so L dot is 0. Or we can integrate with respect to time, and we find that this tells us twice VP is plus VQ is 0, or VP is minus 1/2 VQ. We don't have to integrate. We're just doing velocities at this point, not positions. So the velocity of P is minus 1/2 the velocity of Q. If we take the time derivative of this, the acceleration of P is minus 1/2 the acceleration of Q. Okay, so by writing this constraint and then differentiating, we were or solving actually, then we were able to find these relative velocities and accelerations. So let's do an example. Suppose there's a police car at point P uh, driving vertically on this road, and you are in a car at point B and you're driving horizontally on this road. And when you see the police car, you start to decelerate. So your velocity is in to the left, and your acceleration is to the right because you're decelerating. So you're moving this way but slowing down. Okay. Um, your car is decelerating at 25 feet per second squared. Uh, the police car is traveling at 35 miles per hour constant and using this radar gun, and they measure your speed at 65 miles an hour when theta, this angle between the vertical and the line between the two cars, when that angle's 22 degrees, they measure your speed at 65 miles per hour. Question is, how fast are you really going relative to the stationary ground? Okay, so we'll use the roads as our stationary frame, and then we'll set up a moving frame as appropriate. So we let VB be the speed of car B, and that's what we're trying to calculate. So the velocity of B relative to P is velocity of B minus the velocity of P in the vector sense. And the velocity of B is minus VB in the I direction. That is, it's going in the negative x direction with a magnitude VB. And the velocity of the police car is positive VP in the J direction, but we're subtracting that, so we get minus VPJ. So the orientation of this line is the unit vector along that line connecting the two cars, and it's just sine of theta I plus cosine of theta J. And so the velocity if we let VR be the radar speed measurement, then since PB is decreasing, that is the two cars are getting closer together, then minus VR is the velocity B relative to P dotted with the unit vector between the two, okay? And if we do that, then we get minus VR is minus VB sine theta minus VP cosine theta. And we can use these, combine these to solve for VB, and we get VB is VR minus VP cosine theta over sine theta. We know the angle is 22 degrees, we know the velocities, and that gives us a velocity of B of 86.9 miles per hour. Okay, and then the acceleration of B is the acceleration of P plus the acceleration of B relative to P. And P is traveling at constant velocity, so it has no acceleration. So the relative acceleration is just the acceleration of B, and it's 25 feet per second squared. One more problem. It's a piston problem. So in this case, point A is fixed. Then there's an arm linking point A to point B, and the arm is rotating. Okay, and then there's an arm from point B to point C, and it's rotating. And so if you force point B to go around in a circle, then this piston will go up and down, and it's constrained to lie on this vertical axis. Okay, so the idea is that piston head C is constrained to move vertically. The crank AB is rotating counterclockwise around this way at a constant angular velocity of 2,000 rotations per minute. The radius of this arm AB is 3.5 inches. The length of this arm here is 5.3 inches, and we'd like to know the velocity of C when theta, this angle here between AB and the vertical, is 35 degrees. So we can take this triangle here ABC and use the law of cosine. So this length squared is this length squared plus this length squared, this length we call YC, minus 2RYC cosine theta. Okay, we can solve this for YC using the quadratic equation. We get this with a little, if you think it through a little bit, then you find you have to use the positive term here, okay? we have two solutions. We want the positive one. So yc then, this distance, is r cosine theta plus L squared minus square root of L squared minus R squared plus R squared cosine squared theta. So this relates, this gives you yc in terms of r, L, and theta, strictly geometry. Now we can take the time derivative of this. Yc dot is minus r theta dot sine theta minus r squared theta dot sine theta cosine theta over this square root. And we know all these things, so we can just plug it in and calculate it. So again, this is one of these cases where you're writing a constraint and then differentiating to solve a problem. If you put in the numbers, the velocity of the piston is minus 55.5 feet per second. Okay, and again in the vertical direction. So it's moving down at 55.5 feet per second when theta is 35 degrees and we're moving clockwise. All right. So those are some simple examples of the use of relative motion to solve problems.